Hi, and welcome to the Learning Zone. This is Mr. B. In this video, I will explain how to perform calculations using the ideal gas law. The ideal gas law is based on the kinetic molecular theory, which states that gases consist of small particles, atoms, or molecules that are in continuous random motion. The volume of the particles is negligible. The intermolecular force of attraction is also negligible, and no energy is lost due to collisions, but energy is transferred. Therefore, the collisions are called elastic. The ideal gas law may be written as follows, where P times V is equal to N times R times T, where P represents the pressure of the gas in atmospheres, V represents the volume in liters, N represents the amount of the gas in moles, R represents the universal gas constant, and T represents the Kelvin temperature. The ideal gas law may be rearranged. For example, to solve for the pressure of the gas, simply divide through by V. This will yield the following, where P is equal to nRT divided by V. To solve for the volume of the gas sample, divide through by P, where V will equal nRT divided by P. To solve for the number of moles, divide through by RT, where N will equal PV divided by RT. To solve for the Kelvin temperature of the gas, divide by NR, where PV divided by NR is equal to the Kelvin temperature. And to solve for the universal gas constant, R, divide PV by NT. The universal gas constant R represents the conditions of an ideal gas at STP, where R is equal to P times V divided by N times T, where P represents 1 atmosphere of pressure, V represents 22.4 liters, N represents 1 mole of the ideal gas, and T represents 273 K. The numerical value for R, therefore, will be 0.0821 atmospheres times liters divided by moles times K. At some point, you may be required to perform conversions involving pressure and temperature. To perform pressure conversions, consider the following, where 1 atmosphere of pressure is equal to 101.3 kPa. 1 atmosphere of pressure is also equal to 760 millimeters of mercury, or 760 torr. To convert pressure in kPa to atm, which is required when using the ideal gas law, divide the given pressure in kPa by 101.3 kPa per atm. If the pressure is given in millimeters of mercury, or torr, divide the given pressure by 760 millimeters of mercury or torr per atm. To convert the Celsius temperature to Kelvin temperature, we simply add 273 to the given Celsius temperature. Remember, when using the ideal gas law, the units used during a calculation must be consistent with the units of R, which are atmospheres, liters, moles, and Kelvin temperature. Now let's use the ideal gas law to perform some simple calculations. Consider the following example. What is the pressure in atmospheres exerted by a 0.500 mole sample of nitrogen gas in a 10.0 liter container at 298 K. First, we write the ideal gas law. P times V is equal to N times R times T. Solving for P generates the following, where P is equal to nRT divided by V. Now we insert the data. 0.500 mole times 0.0821 atmospheres times liters divided by moles times K times 298 K divided by 10.0 liters. Clearly, the units of moles, liters, and K will cancel, and the pressure will be 1.21 atmospheres. Now let's use the ideal gas law to perform a volume calculation. Consider the following example. What is the volume in liters of 0.250 mole of oxygen gas at 20 degrees Celsius and 740.24 mmHg of pressure? Clearly, in this example, conversions must be made for pressure and temperature. To convert the pressure to atmospheres, we divide 740.24 mmHg by 760 mmHg per ATM. This will equal 0.974 ATM. To convert the temperature to K, we add 273. 20 degrees Celsius plus 273 will equal 298 K. After writing the ideal gas law equation, PV is equal to nRT, we may rearrange to solve for V, where V will equal nRT divided by P. Inserting the data, V will equal 0.250 mole times 0.0821 atmospheres times liters divided by moles times K times 298 K divided by 0.974 ATM. Clearly at this point the moles, the atmospheres, and the K will cancel, and the volume of the sample will be 6.17 liters of oxygen gas. Let's end the lesson with the mole calculation. Consider the following. What mass of chlorine gas, Cl2, in moles is contained in a 10.0 liter tank at 27 degrees Celsius and 354.55 kPa of pressure? Clearly, the first step in solving this practice problem is to convert the pressure to ATM and the temperature to K. To convert the pressure, divide 354.55 kPa by 101.3 kPa per ATM. This will equal 3.50 ATM. To convert the temperature to Kelvin, add 27 degrees Celsius plus 273. This will equal 300 K. After writing the ideal gas law equation, PV equals nRT, we may solve for N, where N is equal to PV divided by RT. Now inserting the data. N is equal to 3.50 ATM times 10.0 liters divided by 0.0821 atmospheres times liters divided by moles times K times 300 K. In this case, the ATM, the liters, and the K will cancel, and the mass in moles will be 1.42 mole of chlorine gas. It is important to remember that the ideal gas law is representative of an ideal or perfect gas. When using the ideal gas law to perform calculations involving a real gas, the true values of pressure, volume, Kelvin temperature, and moles may not truly represent those of the real gas. To determine the actual values of a real gas, one should use the van der Waals equation. This concludes my explanation of how to perform calculations using the ideal gas law. Hopefully this video has been helpful. Thanks for watching.